Yaskawa.
Welcome to the MP940 MotionWorks Plus Transition e-learning video. Hi, this is Matt Pelletier here at Yaskawa, and before we get started, I would like to go over some prerequisites. First, I'm assuming that you're familiar with the MP940 hardware and MotionWorks Plus environment. I will be giving you a few reminders about how you programmed in MotionWorks Plus, but I want to concentrate on explaining how to get the job done in the IEC environment. I'm also assuming that you are relatively new to the IEC 61131-3 standard, to Sigma 5, and to the MP2600 IEC product. But for this training, I do hope that you already know something about the MP2600 IEC. So before watching this e-learning video, could you please run through the MP2600 IEC hardware overview e-learning module, just so you can get up to speed on the product itself. And then also, I'd highly recommend you watch one of the Quick Start e-learning videos. These Quick Start videos give you a feel for the MotionWorks IEC software that I'll be demonstrating with here. And our library of e-learning modules and e-learning videos continues to grow on both the MP2000 IEC series and with Sigma 5. So any of these resources that you can find in the product page will be helpful and applicable to this training. The objective of this training is to help make your transition from MP940 and MotionWorks Plus to MP2600 IEC and MotionWorks IEC to make it smooth. You've got to understand that there's no magic button that just converts one to the other. And while all programming functionality of the MP940 with MotionWorks Plus can be transferred to the MP2600 IEC, some of that functionality requires a bit of extra attention. So it's my goal in this e-learning video to bring these topics to your attention so that you, as the OEM or end user especially, can quickly come up to speed on Yaskawa's new IEC controller platform. What I want to do is help you avoid the pitfalls and alert you of some of the programming differences and details. And I want to help you use what you already know about MotionWorks Plus and the MP940 to give you a head start with the IEC platform. And one thing you'll see that this e-learning video is not intended to be is a step-by-step how-to video like many of our other ELVs are. We want this to be an overview of the topics, giving you simply an orientation to the specific areas of attention when converting from MP940 to MP2600 IEC. So I hope that you find it informative, and I will be showing some basic navigation but not explaining every single click. Now, before diving into the material, I would like to just outline the sections of this training, which you can also see reflected in the navigation panel at the left. I'll cover some general programming concepts, followed by configuration, homing, indexing, camming, and networking. And I'm not going to take the time to cover every single property of every single MotionWorks Plus block, as really this e-learning video is not intended to be an exhaustive reference. I will instead use examples in each of these sections to illustrate the major concepts. So let's begin. A general comparison of the programming concept I think is a good place to start. You'll see that there are many similarities and several differences in the instruction set, the programming method, variables, system variables, startup tasks, programs, and subroutines. First, let's look at the instruction set. Your programming tools are generally the same in both environments. Here in the MP940, you have your list of commands, and of course each of those have their properties. And in MotionWorks IEC, you also have the list of commands. The difference is that in MotionWorks Plus, this set of commands is specific for Yaskawa, but in MotionWorks IEC, the instruction set follows the international programming standard of IEC 61131 and PLC Open. And part of this standard is that we don't have the properties as you'd have in different blocks in MotionWorks Plus with the properties area. Instead, you have the inputs as the properties, basically visible right on the block itself. The blocks in MotionWorks Plus typically have one input and one output, sometimes two outputs. And the equivalent for that in MotionWorks IEC is the execute and done input. You'll pretty much always see an execute in most of the blocks. Block calculations, status, and diagnostic information is also given in these outputs of the block. And as the program runs, then you can monitor the state of both the inputs and outputs right on the code page, and you don't have to have a separate monitoring program and monitor it by block number as you did with the MotionWorks Plus environment. In MotionWorks Plus, you'd connect the blocks in the sequence that you wanted them to run. And the same is true with IEC, but IEC gives you a lot more flexibility. You don't have to connect the blocks together to sequence them, as they'll also be executed on the page from top to bottom and left to right. And in MotionWorks Plus, did you ever have to make a complex network of if blocks in order to accomplish what you know you could have done in ladder with just a few rungs? Well, in MotionWorks IEC, you can combine the best attributes of all of the major types of programming languages. You can use ladder, function blocks, structured text, instruction list, and even sequential function chart, which is like a top-level flowchart language. As you can see, in all, there are 5 programming languages available, and you as the programmer can choose which language to use for each program worksheet. Variables are another area where the MP2600iec expands functionality. In MotionWorks Plus, every variable you made was a global variable, but the MP2600iec supports both global and local. And if you're creating a function block, you can also have input and output variables. Global variables mean that once you name a variable, that name refers to the same variable everywhere in the entire project. This may be the way you want the variables to work, but is a programming limitation. Here's an example. Let's say you want to reuse a section of your program, and it should run independently of the original. With global variables, you would copy, paste, and then have to manually go in and change all the variable names, which can make it very difficult then to reuse your code. When you have local variables, then you copy the code and the variables from one program page to another, and the variables retain their names, but still operate independently. And there's then no name changing required. This is one of the major goals of IEC programming, which is code reusability. Additionally, when defining a variable in MotionWorks Plus, you may remember that you had the 4 data type selections: bit, integer, long, and float. Now the IEC standard has these as well, just uses slightly different names here: bool, int, dint for double integer, and real. And you can see that here in a variable list. If you look at your variable list, there's also a type. And the list goes on and on and on and on. Very many data types, which is one of the hallmarks of IEC 61131-3, and we call it strong data typing. It really just means that the variables of different data types will then not mix unless the programmer converts them to the same data type. There are 13 elementary data types, and you can make your own data types, which is how you create structures, arrays, or enumerated types. Continuing on with variables, let's discuss the MP940 system variables. These are prefixed with the S for setting, and if you look down here, some of them are M for monitoring, and contain a lot of important different information such as error levels and feedback data. The MP2600iec employs this same concept, but instead we use the PLC Open term parameters instead of system variables, and each parameter then has a number associated with it. So to use this information in your code, you use this block called MC read parameter or write parameter to set. That's how you would deal with this type of important system information. Now that we've discussed programming, let's look at how the programs run in the hardware. In the MP940, each program has an auto start property. And then typically the programs with the auto start would stop and start other programs in the code using the play and pause icons. Now this fundamental concept is different in the MP2600iec. The MP2600iec executes all its programs continuously, scanning through them each at the defined scan time or interval. which you can see set here. Normally it's set to 10 milliseconds. One program cannot start or stop another. Now that doesn't mean that you have to run every block of every part of the code all the time. It just means that you can use conditions such as if and jump statements to make different variables true and false at different times so that the blocks run when they're supposed to. And there's really more to the story of controller architecture, which has to do with the tasks in which the programs run and are executed by the controller. In MotionWorks Plus, each program scan type is assigned to either high scan or low scan. These are the only two tasks available in the MP940, with low scan and high scan. And the task update rate is set here in the system properties. But the MP2600 IEC follows the IEC 61131-3 definition, which is, again, more powerful and flexible. And this allows up to 16 tasks using the Pro version, as I've got here. And each task, I don't have 16, I have 1, 2, 3, 4, 5, 6 tasks at this point. And each program is assigned to a specific task in the hardware tree. And then you can have different update rates or settings for each task. This one's 100 milliseconds. This one is 80 milliseconds. This one is 50 milliseconds. So very similar here to the high scan and low scan, but you have basically high, low, and everything in between. And this model also allows for special tasks that run just once, like this one right here, the initial system task, which is set in this case to warm start, basically a power up, so that you can have system data initialized right when the controller turns on. And we have a lot more information about MotionWorks IEC Pro and the task assignment and how to do all that in the MotionWorks IEC Pro e-learning module available on our website. So as the programs are running, each in their tasks, what if there's another code page that needs to be executed at that time? This in MotionWorks Plus is called the subroutine. And subroutines in MotionWorks Plus are basically just program pages that run only when called by another program or another subroutine. In the MP940, you have to be sure, as we've done here, to call them only one at a time. And basically all a subroutine is a way to organize your code from one page into another page so that you don't have all of your code on one huge page. You would never call the same subroutine more than once, since the data would become corrupt. This is because, as you remember here, subroutines work with all of the data, all of the global variables, with all of the current values. In the MP2600 IEC, we don't use subroutines. Instead, we use function blocks. Remember, all of the program POUs are running all the time anyway. So when there's a specific page of code to run at a specific time, so here I've got this function block called simple jog. I can double click on it. Inside you see the code for it. And one nice thing about function blocks is that you can execute them simultaneously by any of the program POUs that are running, because they don't share the same data space like the subroutine does. And this is one of the most powerful features of the IEC programming platform, which is the ability to make function blocks based on function blocks to higher and higher programming levels. This allows you to reuse your code without having to go through and rename variables and make other code changes. So as an example here, I can add this subroutine that I made called simple jog over and over again without worrying about that calling the subroutine more than 2 times. That's exactly why they give different titles at the very top of it here, 1, 2, and 3. The point is, once you have made a working function block, you just keep plopping it down like this wherever you need it in your program as if it were any other instruction, and the function blocks that you make in one project are very easily accessible by another project, so there's really no reworking what's already been done. Now that you've seen some of the general differences, let's look more specifically at the configuration. And configuration means the hardware settings, such as user units, servo parameters, and network devices. This configuration is likely to be for you the first area to consider when you're converting an MP940 MotionWorks Plus application over to MP2600 IEC. The MP940 project contains the configuration folder with the system parameters and system properties. Let me just remind you where that is: the configuration folder, system parameters, and system properties. And I'll start with the most basic of these, the system properties. The equivalent of the system properties in the MP2600 IEC is the hardware configuration. That's this MWCT button. Now this MotionWorks IEC hardware configuration is a separate window where you define basically all the same information that you would have seen in MotionWorks Plus system properties. And the basic navigation difference was that in MotionWorks Plus we had different buttons, each with their properties. In the bottom right, we use a more modern tree structure here at the left for the different devices in MotionWorks IEC. So let me take some time now to look at each of these different sections and relate them from MotionWorks Plus over to MotionWorks IEC, and hopefully help you avoid any pitfalls. So the first area is the SGDH, or the Servo Pack System Properties. And this is where you have all of the parameters of the drive, the Servo Pack, listed numerically. The equivalent of this in MotionWorks IEC is the Sigma V, and then go to the All Parameters tab at the far right, and you'll see all of the same types of parameters. Now, many of these SGDH parameters correspond between Sigma 2 and Sigma 5 used in MP2600 IEC, but the most critical ones for your application are going to be the tuning-related parameters. Now, for tuning-related parameters, it makes the most sense, since you have Sigma 5, to use the advanced features of the Sigma 5. Don't just try to transfer those tuning parameters over. You're probably not going to get a very good result. Now, if you did have a lot of different servo parameter settings in the MP940 system, or you're just not sure, you want to be very sure that you didn't have any other things like torque limits or other settings, and you want to see what they are, you might want to try using the Sigma Win Plus parameter converter. And so basically what you do with Sigma Win Plus is connect the serial cable to the SGDH, pull out the parameters, save them to a file, and then under this parameter converter menu, you can go find that file. I've got a sample one here, and give it something to save it as. Hit convert, and then it will show you parameter by parameter the conversion and give you a little key here for which ones are different, which ones don't apply by the color key here. So you can look at those one by one and decide if you really need to address that parameter, what that parameter is. There's probably going to be many parameters that haven't been changed and that you don't need to worry about, or tuning parameters that you should not try to convert from Sigma 2 to Sigma 5. Moving on now to the MP940 properties in MotionWorks Plus. That consisted mainly of the mechanical system definition so that you could program the natural units or user units. MotionWorks IEC uses the hardware configuration tab. So here in the configuration tab, you'll find the exact same machine cycle, feed constant, gear ratio, user units, load type. And our development team has tried to be sure that we named these the same as they were in the MP940 with MotionWorks Plus. So all of these same names basically port directly over. And you can use the same values in the MP2600 IEC project as you had in the MP940. Now, you will find fewer fields. For example, you're not going to have the encoder resolution, since now in Sigma 5 with the MP2600 IEC we can detect that automatically. But all the rest of them, if you find it in MotionWorks Plus, you can plop it right here into the configuration tab of the Sigma V axis under Motion Engine. If your MP940 application relied on the serial port, the DeviceNet port, or the Mechatrolink port, then there's going to be some engineering required in this area in order to transition to the MP2600iec. Remember that the MP2600iec exclusively uses the Ethernet port for all of its network communication. So if you can upgrade your network devices to use either Ethernet IP or Modbus TCP or even the OPC protocol, that would be the best option. But if it's not an option, there are third-party conversion devices available, and I'm going to have more on this in the networking section of the e-learning video. The final area in the MotionWorks Plus configuration is the external encoder. And MotionWorks IEC basically shows that same information under the external encoder in the hardware tree. So here I go down to controller I/O, external encoder, and you'll see the same type of terms: machine cycle, feed constant, user units, gear ratio, load type. Again, word for word identical to the MotionWorks Plus area under external encoder properties. The other really important part of the MP940 with MotionWorks Plus configuration was the system parameters. And these were just very few, consisting of servo loop gains and limits. The MP2600iec does have tuning gains, but remember, tuning is not usually required thanks to the advanced Sigma 5 tuningless mode. And if you do need to fine-tune the motor, like we mentioned, don't transfer the tuning values over, and don't try to set the tuning values manually. Instead, connect Sigma 1 Plus and use the auto-tuning sequence on your Sigma 5. So what I'm trying to say, don't use the P gains, don't try to transfer those over to the MP2600iec project. This brings up another really important difference in the way these two controllers interface to the amplifier. Let's look here. The MP940 operates by sending a digital speed command over the dual port ramp connection, which means that while the Sigma 2 closes the torque loop and the speed loop, the position loop physically resides in the controller card. That's why the MP940 controller system had those parameters for position loop proportional, integral, and feed-forward gains. The MP2600iec instead commands position straight from the profiler over dual port RAM into the position loop of the amplifier. So you can see all of the gains physically reside in the amplifier for torque, speed, and position. What this means is that you can take full advantage of all of those Sigma 5 powerful tuning options. As I've been mentioning, the tuningless mode, advanced auto-tuning, vibration suppression, anti-resonance, all of these are now available when using the MP2600iec. And this also means that there are no gains at all in the option card. The profiler position just comes out to the Sigma 5 amplifier. Sigma 5 takes care of the rest. Now, just to finish off the system parameters, there is a couple of them here: P-limit positioning error and P-limit speed, which aren't exactly tuning related. We do have the equivalent parameter settings in the MP2600 under the Limits tab. So here in the hardware configuration, under your limits, when you set these, please pay close attention to the setting units, because they're not going to be the same as in MotionWorks Plus. Here you've got PN520, which is the excessive position error alarm level, and PN407, the speed limit during torque control. These are the equivalents in MotionWorks IEC compared to MotionWorks Plus. Configuration differences in these two platforms affect some fundamentals of the programming concept. The blocks in MotionWorks Plus, with few exceptions, apply only to the main servo axis of the system, the Sigma 2 motor. Gearing and camming in MotionWorks Plus assumed that the external encoder was the master, and the virtual master could be selected with the system variable S external mode, and this virtual master had very little control. Only the acceleration and the speed could be set. In the MP2600iec, the external encoder and virtual master are configured as axes in the system. You can see these here. The motion engine shows the different axes of the system. You have the rotary, the virtual axis is another axis. There's also the external encoder, exists as another axis. And so to differentiate between the different axes, you include an axis number, even on this single axis controller. So an important configuration step is to bring these axis numbers into the programming environment. One place where it's easy to get a summary of all the axes and their numbers is in the controller web page under Machine Operations. And you can see the numbers here are axis 1, 21, and 26. This axis number is referred to using a variable with a structure data type called axisRef, just like we show in the Quick Start video. And so here, like in the Quick Start video, I've created a separate text program and I define the axis with this corresponding axis number. Typically it will be as in this example. The Sigma 5 is axis 1, external encoder is axis 21, and the virtual masters are 26 and above if you have more than one. Once that's set up, you can basically forget about the numbers and just connect the variables. Here, Sigma 5, external encoder, virtual master. And for this example, what I have is I'm reading the actual position of the Sigma 5 axis, the external encoder axis reading the actual position, and virtual master reading the actual position. Homing routines can be as varied as the machines themselves. So I want to compare the homing blocks available in these two systems and then present a simple example of homing to a sensor. MotionWorks Plus has one type of pre-designed homing available through the home block. The home block moves the axis until a bit such as an input or other condition is satisfied, and then continues to move the motor to the index pulse of the encoder. Setting the final position is done through a separate block. And if your MP940 based machine required any other type of homing, such as homing to a sensor only, or homing to over-travel sensors, then you would have constructed that customized homing routine block by block. This block by block concept is the technique employed by the MotionWorks IEC environment. In order to build your custom homing routine, Yaskawa has two of the most critical PLC Open homing blocks, which start with MC step. It's MC step limit switch, MC step ref pulse. And these can be found in the PLC Open Plus area as MC step limit switch, step ref pulse, and there's also a set position, which corresponds with the set position block of MotionWorks Plus. And there's also one more here called MC finish homing, which may be used to leave homing mode. In my example, however, I'm not going to use the MC step blocks. I just need a simple home to sensor. So let's look at it in MotionWorks Plus first. In this example, I have an input that will start the motor jogging, and then another input which is tied to a sensor to stop the motor from jogging. There is then a timer to wait 100 milliseconds before the motor moves an offset distance, and then we call that final position, position 0. In MotionWorks IEC, there's almost a block-for-block correlation between these two programs. The only difference is that the rising edge input to start and then to stop based on the sensor are found directly on the PLC Open blocks. It's also worth pointing out here that the timers use the time data type, so both literal and initial values use this type of syntax, T-pound 100 ms for milliseconds. And as we mentioned before, you can see how the PLC Open blocks put other properties as inputs, such as the home velocity and the XL, decel, and direction. And additionally give the diagnostic information as outputs. And so this is my example. You'll see that indexing or positioning really matches up pretty well too, just like homing did. The main differences here are that PLC Open relative and absolute moves use separate blocks, and also direction for the absolute positioning and move complete are handled a little bit differently. So here's an example of probably the most simple indexing move possible in the MP940. Assuming the servo is on, an input triggers the move, and then the subroutine just waits until the motor's in position before it's done. MotionWorks Plus gives you a single move block, and then you choose in the properties the move type, whether absolute, relative, or rotary shortest. In MotionWorks IEC, we have two separate blocks, one for relative and one for absolute. Notice that the absolute block uses the input position and the relative block uses the input distance. Also notice that it's only the absolute block that has the direction input. So the concept is the same in both controllers. When the load type has been configured as rotary in your system properties in MotionWorks Plus, then you're able to choose rotary shortest, and this rotary system can then move to a specific position by moving either forward or reverse. The easiest way to apply the equivalent of MotionWorks Plus rotary shortest option in MotionWorks IEC with the move absolute is to type in MC_direction pound shortest way as the direction input. Let me show you how that works. So on the direction input, we type MC_direction pound shortest underscore way. In MotionWorks IEC, the direction input of MC_move absolute has four options, and one of them is shortest way. These four direction options are wrapped up into a data type called MC direction. You can see this in the data types folder by opening up motion block types, and you see right at the top your MC direction and all the different types of directions that are supported. And you notice that there is one fourth direction that would be applicable to a rotary mode, which is the current direction. That was something that we did not have in MotionWorks Plus. The other difference between the move blocks of MotionWorks Plus and MotionWorks IEC is what it means for the block to be complete or done. As you remember, there is an option here, wait for completion, true or false, in MotionWorks Plus. And what that means in MotionWorks Plus is wait for the motor to get to the final position within a certain completion window. You can also monitor that through the position complete bit. However, in MotionWorks IEC, MC move blocks are done as soon as the profile is complete. This means that the profiler just finished commanding the move. Does not mean that the motor is actually in position. So it's a little bit different. And so I've illustrated that in this timing chart. It's a bit exaggerated, but what this shows is that there's a difference between the commanded profile being done, as we'd use in MotionWorks IEC, and then the actual profile. The motor is going to perhaps be a little bit behind, and the move would be complete at that time. Now, in many applications, the timing difference here is negligible, since the Sigma 5 follows the commanded profile so well, even without additional tuning. But when it's very critical to be sure that the motor has completely stopped moving and that the motor is truly in position, you're going to want to add some kind of complete functionality like we had in MotionWorks Plus. So here's one easy method to make the MC_move relative or absolute perform with position complete, just like in MotionWorks Plus. You'll use the AX1_pset variable ANDed along with the done bit to create your position complete bit. So I've got that here in my code. AX1pset is a variable that becomes true when the position error falls below the level set in parameter PN522. Parameter PN522 can be found under Sigma 5 All Parameters tab, 522 Position Completed With. And now this bit here, pset, can turn on even while the motor is moving, so that's why you want to AND it with the done bit in order to get your position complete. This table summarizes the parameters required for wait for completion. And notice that the equivalent here, S position completion window, was set in the user units in the MP940 PN522 we just showed was set in encoder counts, the post-quad encoder counts of the motor. And also in the MP940 we had M position complete, which was a bit that told you whether you were in position or not. And with the MP2600 IEC, you have to AND together the AX1 preset with the done output of the specific block that you are using it with. And that's how you'll get true and false to know when the move is done or not. Now, one problem that can arise when you're using position complete is that if your tuning is not good enough, or if this in position completion window was set too low, your motor might never make it to the final position, and then the move would never be complete. And so this is one of the benefits of using the PLC Open standard in MotionWorks IEC. Using this profile done is truly more flexible, because then it allows the application programmer to add code for what in position is for that specific application. For example, maybe in position in your machine should latch once the motor crosses the finish line, if you want to put it that way, actually gets specifically accurately to the final position instead of just looking for an in position window. Or maybe the motor has to remain stable at your final end zone for a certain amount of time. Whatever the situation may be, you can build that and then wrap that up into your own function block in order to develop a very machine-specific move block instead of just making do with predefined move complete as we have in MotionWorks Plus. CAMing applications can be widely varied and are often complex, not only in the calculation of the CAM table, but also in the programming logic that automates the engaging, the disengaging, scale, shift, offset. So as in the other sections, here I'll give a general orientation and I'll go through an example of converting an MP940 CAMing application in the case where Yaskawa's CamTool software was used to generate the CAM table. Yaskawa's electronic CamTool software can be used to create a CAM table for both of these controller systems. I would like to start by reviewing the process of including a CAM table for MotionWorks Plus and then outline the process used in MotionWorks IEC. For MotionWorks Plus, we start with the electronic CamTool software and produce a CDD extension file. Then in MotionWorks Plus, there is an area to define tables, and you define a table according to that CDD file. It pulls the data from the CDD file. Then when you use the CamIn block, you set the CamIn block properties to select the appropriate CAM table. Then when you compile and download, the CAM information and your program all get sent to the controller. In MotionWorks IEC, we also start with electronic CamTool. We also produce a CDD file, but then also produce a CSV, comma separated value file. This CSV file gets sent directly to the controller using the MotionWorks IEC hardware configuration. Then in your program, we'll be able to use that CAM file, that CSV file name, with one block called the YCam file select, and then CAMing is engaged with the YCamIn block using the same CAM table ID that had been generated by the CAM file select. So you can see in both cases there is a path for the CAM data to get from the CAM tool down to the controller and then to be used by the program. So the process is very similar for both systems, but there's more to it than just making a quick CSV file in CamTool. This is because there's some differences in the way that units are handled when you are going from MotionWorks Plus to MotionWorks IEC. In MotionWorks Plus, the master unit in the CAM table could really be any value, and it would be then normalized to the machine cycle of the external encoder. And then the CAM table, the slave unit of the motor itself, could have been programmed in either encoder pulses or in the natural unit, the user unit of the machine. We often, for accuracy's sake, would recommend to use encoder pulses for the slave in the MP940. But in MotionWorks IEC, we are going to be consistent here with the units. And you set up your unit for the master, the external encoder, in the hardware configuration, and that is the unit used in the CAM table always. And then the slave also matches the servos unit that's been set up. So it's possible that your table from MotionWorks Plus is in completely different units than what you need for MotionWorks IEC. And in MotionWorks IEC, we can very confidently use these user units. There's no performance decrease based on any resolution differences like we had in the MP940, because this controller uses 64-bit floating point operations. So how about I explain this again by means of an example. Let's consider for my example a machine with a rotating shaft, and the controller's job, this first case it was the MP940, its job was to move the servo motor in a motion profile path synchronous to this master shaft. And in my example, that follows the blue path here, moves it out a bit, pauses and keeps moving out, and then moves back. The total distance is, as it says here, 4 inches out and back. And that has to happen every 450 degrees of this master shaft. So a little bit more than a complete revolution. Every 450 degrees, you can see that the master shaft here in red goes back to position 0. Let's show a little more detail here about this machine. And you can see that in this case, to get this master shaft rotation information into the controller, we use an encoder. This is an encoder with 400 pulses per revolution, not too much, but it is on an induction motor through a ring kit, driving a 4-to-1 gearbox, so that the master shaft here has an effective, actually 1600 pulses per rev from the encoder because it's running through this gearbox. And I'll spare you the mathematical details here, but I have outlined it up here in the top right, showing that that 450 degree master cycle, the 1.25 turns of the shaft, equates to 2,000 pulses from the encoder. And on the follower, the slave side, that 4-inch out and back move, based on the mechanical system properties of the slave, turns out to be 9,306 pulses. And those are pulses of the servo motor encoder. And these are the kind of calculations that were likely to have been made when the application with the MotionWorks Plus and the MP940 was originally designed. The configuration settings can and should be verified as we discussed earlier, and you'd want to set those in the hardware configuration. So let me just verify here in this example. I have configured the external encoder as load type rotary with a feed constant of 360 degrees. That's 360 degrees per load shaft revolution. The machine cycle is set to 450 degrees, outlined in red. And the encoder resolution, outlined in purple, is 400. And the gearbox is 4-to-1, input to output 4-to-1. Also, if we look at the follower, which in the MP940 system shows that the feed constant is 5, and the gear ratio here, input to output, is 142 to 100. It's 1.42 to 1. Same thing here, 142 to 100, feed constant of 5. And since this is a load type linear on both of these, the machine cycle doesn't really matter. It's only for rotary applications that even need machine cycle. The next step then is to open CamTool and find the CamTool file. So in CamTool, I have my project file name here. It's going to be inside the project folder, and you'll want to look for file type CDD. This is the name of my file. And then, good practice, whenever you are going to make changes to a file, you want to save it as a new name. And I'll call it MP26 underscore IEC. You can save it in the same folder, it doesn't really matter. You'll save position data. And it's good practice to use an 8-character file name for both the CDD file and the CSV file. The CSV file has an 8-character limit for sending to the controller. So once this CAM file is open, now you need to go to the set style and check out the unit of the phase, meaning the master, and the maximum. Let's go ahead and look at that. So we go to the graph menu, set style. I can tell right away that the master cycle is set for 2000. And not only does it say pulses, I know it's 2000 because it doesn't make any sense for that to be 2000 degrees, would be my other option. So the number I wanted here was 450 degrees. So I'll select no unit and 450 degrees. Now don't select degrees, that will limit you to 360 for the max phase. So set no unit and 450, which in my example is the maximum. On this same page, you want to look at the unit for the slave. It should also be set to no unit, and then instead of pulses, put in the maximum for the slave. So here I am, I see I've got the 9306. That's obviously not inches, plus it says pulses. I'll go to no unit and type in the 4 inches, which was the maximum out. Now it may be that you already have this value in inches, and if that was true in MotionWorks Plus, then you would also have had this ball screw and gear ratio information plotted out. MotionWorks Plus was able to use that information to basically calculate the pulses in the end anyway. So it's possible that you did have this position also in inches. However, it's probably more likely that you have it in pulses directly. And then you click OK to renew the data. Now when I accept these changes, you can see the graph data is kind of gone. So now in set parameter, you'll have to also possibly scale the endpoints of the cam profile back from pulses to inches. And so from the graph menu, I'll go to set parameter. And you see here's the different sections of the cam table. I had my follower endpoint set in pulses. So I'll need to have halfway the 2-inch stopping point, and then the final 4-inch maximum out point. Put in 2 and 4 instead of having it in encoder pulses. I'll just point out this master plotting is automatically recalculated when you change the master cycle from 2000 to 450. So whatever you change it to, you don't have to touch anything with master plotting unless you want to remake the cam table. I just want to have an equivalent cam table with the same number of points. So I'll click OK, renew the data, and you see the graph again. And on this graph I can verify that I have the position here in inches up to 4 inches. I have the phase here in degrees up to 450 degrees. So that was the last part that we had to do here, was changing the follower endpoints if you had been using the pulses in the set parameter screen. So now finally in CamTool I just have to save the file. We recommend you save the CDD just for future reference if you need to pull it up again, and then also save the CSV file. That's the one you need to upload into the controller. So let's do File, Save, and it's already in there. Just hit Save again, save over, and then File, Save again, this time save as CSV file, and I just keep the same name. Save the position data always. Now, just to finish up this example, we'll go to the hardware configuration and send the CSV file to the controller. And one thing I like to do is, even in the controller web page, you can see that that file's in the controller or not by looking at the project archive. You have to log in as admin. Look at project archive. You can see the list of the files, and I don't have any CSV file in this list right now. I'll go over to the hardware configuration, and under the online menu, controller configuration utilities, and you can send the cam data to the cam directory. Click execute and then find the file. There it is, the one that I just made. Open it. Now that it's finished, I can go check and see if that made it to the controller by refreshing. Hit project archive again, and there it is. The CSV file is in the project archive. I usually even highlight that part and copy it as I'll need it in the code itself. So once that file's in the controller, you simply reference the file name and path in single quotes and feed that into the cam file select block. So I'll go now and do that here. Double click on file. Basically just paste in what I had from the web page. And if I put it in quotes, then that's fixed, single quote. So now if I make and run this, okay, I'll download it and run it. Then I can see in debug mode that if I execute cam file select, it's done. It gives a cam table ID of 1. That sends that down here to the cam in block. And all I need now is input 7 to execute cam in. And so by setting it up this way, we're able to have different cam files selected. And then all you need to do is tell this cam in block which cam table ID to use, and it will automatically, basically on the fly, choose between any different cam tables that you want or that have been selected with cam file select. So very powerful camming in the IEC environment. So when I run my cam profile, I can now verify using the software's logic analyzer that everything's working. I'm plotting the slave profile and the master position. To find out more about camming, the shift, scale, and offset functions, how to swap cam tables, or anything else like that, please watch the camming e-learning video, which you can download at the e-learning curriculum portion of the website. For the final section of this training on networking, I'll talk about converting the 3 communication options of the MP940, which are serial, Mechatrolink, and DeviceNet. The MP940 used the network technology of its day with 2 serial ports and a network option of either Mechatrolink or DeviceNet, which could function as either master or slave. The MP2600iec uses the modern technology of its day with Modbus TCP, Ethernet IP, and also OPC, which is a widely used standard communication interface for factory automation, and it's great for communicating to PCs. And so I think you can tell that if you have an MP940 as part of a network in your machine, replacing it with the MP2600iec is going to require some network upgrades or conversion hardware, as well as a bit of engineering to implement this. So let's see what can be done to make the transition. When it comes to serial communication on your existing MP940 system, the first option to consider is just to upgrade your existing serial devices, such as an HMI, to modern devices that support TCP/IP or Ethernet IP. If that upgrading option is prohibitive to your application, then another choice is to use a commercially available Ethernet to serial converter. The serial converter acts as an Ethernet IP master to the MP2600iec and feeds the information it receives from your serial devices to the MP2600iec. Using one of these serial to Ethernet converters as a Modbus TCP master requires a couple steps in the controller. First, you enable the MP2600iec as a Modbus slave in the hardware configuration. So let me show that. Under Modbus TCP, just be sure then that you have checked Enable controller as a Modbus slave, and then you can online send that configuration to your controller. The second step is to add global variables within the address range indicated in the group heading. So as soon as you click Save and send that over, if you come over here and view your global variables, you'll find that there are address ranges in which you are to put the Modbus variables. That act of saving, one thing it does is create these groups for Modbus, different function codes within Modbus. And then what I've done here is manually typed in different variable names and typed in an address using the address range given in that group. So now the data in these variables will be both received and here the outputs sent over Modbus TCP to the serial to Ethernet converter device, which then relays the data to and from the serial device. So I think you're aware that in this solution you are adding another hardware device to the system, and that device is going to require its own configuration. One example, the one that we're showing here, is the Digi1 IAP serial to Ethernet converter. And we've tested that one here at Yaskawa and have documented an example of how to configure it to work with a Red Lion HMI as an example with this document number. MP940 applications frequently used Mechatrolink in order to network multiple controllers together, or may have had network I/O modules for I/O expansion. And we have several solutions for moving from MP940 Mechatrolink networked axes or networked I/O. Multiple MP2600iec controllers can be networked together over Ethernet IP or Modbus TCP, each with their own program, just like the MP940 controllers are networked over Mechatrolink. Now, if it's a true multi-axis application, you might want to consider using one of the multi-axis IEC controllers then, so that you have one program controlling several axes, in this case over Mechatrolink 2. These multi-axis controllers also have additional slots for I/O expansion, and they support Mechatrolink 2 I/O, such as the 64-point I/O modules. And for expanding I/O, all of the IEC controllers support Ethernet IP or Modbus TCP, and so you could replace those devices with Ethernet IP or Modbus TCP I/O devices instead of Mechatrolink. DeviceNet was often used with the MP940 for I/O expansion, and the configuration option that we'll discuss here is when the MP940 is configured as a DeviceNet scanner with I/O devices connected as adapters. So if in your project you look at the system properties and you have the network here configured as a DeviceNet master with any number of nodes connected to the network, then you've got the DeviceNet option configured as a scanner. Now you would have also had in MotionWorks Plus then network data. So under the data network you would have had some number of bytes in and bytes out for each node of different data types, perhaps even single bits coming in and out of each node. To put an MP2600iec as the scanner on a DeviceNet network means that you need an additional device called a DeviceNet master gateway so that you can convert the network variable data from Ethernet IP to DeviceNet. This gateway acts as a DeviceNet master or scanner, but then it's a slave device to the MP2600iec over Ethernet IP. And so similar to the serial to Ethernet converter, the DeviceNet master gateway requires a few steps. You'd have to configure the gateway using the manufacturer's instructions, and then configure the controller to add this gateway as an Ethernet IP device in the hardware configuration, and then finally add global variables. So here under Ethernet IP, I've added the device, in this case the Turk BL67, and looking at the details, you can see the different settings. And so this Turk BL7 is the master of DeviceNet. It's going to be feeding me information here through this area. If I go now to the global variables area, you can see I've got a group that was created when I saved that configuration and gives me an address range at which I can create variables here in Ethernet IP, MotionWorks IEC land, to be sent over DeviceNet through that gateway. And we have done this, and the steps to do that are outlined in the document Connecting the MP IEC Controllers to DeviceNet Slaves. This concludes the e-learning video. I thank you very much for your attention, and I wish you the best in your endeavors with the MP2600iec. And remember, you can always contact us by phone, website, or email with any further questions.